So today's learning objective is all about kind of the properties of quadrilaterals, and kind of we'll talk through some of them. We'll talk about some of the properties. So just a quick recap: quadrilaterals. There's a shape which has four sides, kind of a type of a polygon. Remember, polygon is a shape with more than two sides. And kind of a property that applies to all of these, which we proved last time, was that the sum of the interior angles sum to 360 degrees. And if you remember how we did that, we drew two triangles, and bish bash bosh, we got that. So let's just talk through some of them. The one you're probably most familiar with is a square. So a square has kind of four sides of equal length. We knew that kind of, and four right angles, i.e. 90-degree angles on each of these corners. And the opposite sides are parallel. This side is parallel to this side, and this side is parallel to this side. And the diagonals, i.e. if you connect one corner to the kind of the opposite corner, when they bisect each other, i.e. kind of like intersect with each other, or rather they'll cut each other at 90-degree angles, like that, as you can see there. There's also we can also talk about the rotational symmetry, and you can see that there's four lines of symmetry. There's of course these two diagonals, right? If we flip it, we can see how that works. If we have something like this and this, we can also see that there's symmetry through these lines. So there's four lines of symmetry. We've also got a rectangle, which is very much like a square, except for the fact because the side lengths aren't equal, the diagonals don't bisect at 90-degree angles. But likewise, it has four kind of lines of symmetry. And there we go. I mean two, so the ones in black are the lines of symmetry. This is actually a common mistake students make, is that kind of for rectangles you think that there's four lines of symmetry. The way to convince yourself that there are in fact only two, if you get any sort of rectangle out, so say a sheet of paper, right? So if you take a sheet of paper like this, right, and then try folding the rectangle along its diagonal, i.e. from here to here, right, and you'll see kind of it doesn't really fold, right, into kind of half the shape. So that's why there's only two lines of symmetry. So it can be folded like this, right? Sorry, like this, like that, or like that, and half like that. But it cannot be folded diagonally, as you can see. So that's one way to convince yourself, is actually just get a piece of paper out and try this out. Try out with a square. It works with a square. There's four lines. You can fold it across the diagonal, but not with a rectangle. And kind of we've also got something called a I always struggle saying this, parallelogram. There we go. I always struggle with saying that word. I don't know why. So with this shape, there are kind of two pairs of equal sides, and kind of so the length of this side is equal to the length of this side, and the length of this side is equal to the length of this side. So this is kind of fairly analogous to a rectangle, except for kind of the angles are no longer 90 degrees. It kind of just pushed off its sides, and kind of I guess someone just given a little push here. I guess they've pushed it like that, and it's toppled up. I guess. And so you've got kind of the opposite two sides parallel, and then you've got the diagonals that bisect each other as well. And then bisect each other, that means that when the diagonals cut each other, it turns like this length. It cuts like the other diagonal in half, basically. That's what bisecting means. So I used it back here without explaining it, sorry. When you say the diagonals bisect, is that because the diagonals, when one diagonal cuts the other, it does it in a way that it's kind of, cuts it into half. So i.e. this length is equal to this length, and this length is equal to this length, and kind of they're all equal to each other because it's a square. And see, a rectangle here also bisects the diagonals in kind of to four equal lengths. In this shape, it's not so much a four equal lengths, but it's still bisecting because this length is equal to this length, and this length here is equal to this length here. In terms of symmetry, try this out, see what you can do. Get a piece of paper out if you want to convince yourself of it as well. Pause the video, have a go at this. 1 minute's there, and you're still struggling to find the lines of symmetry. That's because there aren't any. Sorry to send you off on a trick question like that. So if you can see kind of just by if you attempt to try to fold it, etc., you can tell there aren't any. So that's a thing with a parallelogram. kind of almost the analogous, if a parallelogram is analogous to a square, then a rhombus is, sorry, to a rectangle, then a rhombus is analogous to a square, I guess. So you've got kind of 4 equal sides, but again, that this side is parallel to this, and this side is parallel to this one here. And then the opposite sides of a parallel, and the diagonals also bisect each other, but at 90 degrees here. And there's kind of 2 kinds of symmetry. It's kind of this one here and this one here. So if you draw one out, you can indeed fold this over, for example. So that's a rhombus. Now let's move on to a trapezium. The trapezium, it's a pair of parallel sides like this. If you want to calculate the area, this sometimes it does come up. If you have this, the area is, if this side length is A, this side length is B, you go half of A plus B, i.e. the average of A plus B times by the height. And then there's no lines of symmetry, well, not necessarily any. If say this line is kind of almost the same as that one there, then there might be kind of one along the middle. So they can be kind of 0 or 1, I guess, depending on the trapezium itself. And then we've got a kite. So the kite has 2 pairs of parallel sides. Sorry, of two pairs of equal sides. This line is kind of length is equal to this length. This length is equal to this length, and the diagonals bisect each other at 90 degrees. And there's one line of symmetry, which is this one here. You can fold it across there. And that's about it to kind of the properties that you need to know. A lot of the time, you can remember a lot of these kind of, if you just draw out the shape a few times and kind of square or rectangle, that. If you can remember what a parallelogram looks like, and if you think about parallelogram being kind of close to a rectangle, then you think the other one's a rhombus close to square. And with these, I guess there's a bit of memorization involved, but I guess if you kind of see them enough times, you don't even memorize them. It just becomes like lodged in your brain somewhere back there. So try a few questions out on these, just to try seeing if you remember any of these kind of these properties. A lot of the time I have seen questions on these. It turns out to be kind of using them for a purpose, or kind of maybe perhaps proving them in certain circumstances. But it's quite unlikely for you the question to be list the properties of a rhombus, for example. It's far more like you might see a rhombus and have to use some sort of property or something. So hopefully that all made sense, and I'll see you guys in the next video where we'll talk about the properties of a triangle.